Okay, guys. So in today's lecture, we're going to look at another application of derivatives, and in particular, we want to focus on how to compute any limit that comes our way. Okay. So we talked about limits at the beginning of the semester, and we encountered some situations in which we couldn't just plug in directly. And remember, that was indeterminate forms, and situations that we encountered were 0 over 0 and infinity over infinity mainly. Sometimes we saw the 1 to the infinity case. Those were the limits that gave us e to some power. But as I mentioned at some point, there are 7 types of indeterminate forms. And when one of these show up, how do we deal with them? So we didn't talk about it at that point because we needed to know how to take derivatives to be able to give a satisfactory answer to this question. Now that we know derivatives, we can actually address this. Okay, so let's talk about the indeterminate forms of limits. I'm going to present to you here what they are so you can recognize them. You need to know this. And then we're going to talk about the techniques involved to be able to solve this type of indeterminate forms. Okay, so after this, computing limits should not be too much of an issue anymore. Okay, all right, so I guess before we go on, uh, let's talk about what do we mean by an indeterminate form. So here I wrote something that could indicate what an indeterminate form is. So an indeterminate form of a limit is an expression that results after direct evaluation of the limit and from which we cannot conclude what the value of the limit is. In other words, remember the first thing that you do when you compute the limit is you just plug in, okay? And you try to analyze and see what this gives you, what this gives you when you plug in. And indeterminate form is a form so that if that shows up when you compute a limit, you cannot actually decide what the result is from that form. You need to do something else. We saw examples like 0 over 0 and infinity over infinity that you could get different outcomes with the same form. So the moment that you get different outcomes with the same form of the limit, then it's indeterminate because you cannot decide beforehand what the answer will be. So let me just make it more clear via the examples here. So I'm going to I'm going to write down the indeterminate forms so you have them clear. These you need to memorize them, okay? There are 7 of them. You need to be able to recognize them. And then what I'm going to do is show you why they are indeterminate forms. So indeterminate forms we have are 0 over 0. We already know this one. Infinity over infinity. We have encountered these two. And when I say infinity over infinity, remember, it's any combination of positive or negative infinity. Okay? 0 over 0, infinity over infinity. Now we have 0 times infinity. That's also an indeterminate form. Some people will say, well, 0 times anything is 0. Well, 0 times something that is not infinity. So 0 times infinity. Then we have the power like, which are 1 to the infinity, 0 to the 0, and infinity to the 0. Okay? And then there's one more, which is infinity minus infinity. So these 7 forms, so when you take a limit and when you evaluate directly and you obtain one of these forms, these are indeterminate forms, meaning you need to do something else to compute the limit. Okay? If something else comes up, then you can evaluate it. You can decide what the answer is. Like for example, if you get infinity plus infinity, well, that's just infinity because infinity plus infinity is infinity, right? And all that kind of stuff. Like if you get 0 to the infinity, well, that's just 0 because 0 to any power is still 0. You're multiplying just 0 a bunch of times. Okay. Notice that this is different than infinity to a 0. That's a different story. Okay. Okay. So let me show you why these guys we call them indeterminate forms. Again, all I have to do is provide to you 2 limits giving you the same form but exhibiting different results. Okay, and most of the cases are going to be silly cases. In particular, the red limits that you're going to see here are silly cases, and the blue limits are slightly more interesting. And the green limits is just to show you that with the techniques that we currently know, we cannot actually compute them. Okay, the green limits. All right. So for the indeterminate form 0 over 0, let's take a look at the following limit. Limit as x approaches 0 of x over x. This is a silly limit, but nevertheless, it's a 0 over 0 situation, right? By direct evaluation, we get 0 on top and 0 in the bottom. So that's 0 over 0. But of course, this limit equals 1 because you can simplify the x's before you even take the limit, right? So we get 1. How about the blue limit? Certainly, when you plug in 0, we're going to get 0 over 0, right? Because cosine of 0 is 1. So we get 0 over 0. But if you remember, this is one of the special limits. And we show at the beginning that this limit was equal to 0. So here you go. Here you have two limits. Both have the form 0 over 0, but one limit gives you 1, the other one gives you 0. In other words, this is an indeterminate form because by just saying that it's 0 over 0, you cannot decide what the answer is. You need to do something else. Okay? And again, we have this green limit here, which is also 0 over 0, but there is no factoring, nothing that we can do here that will allow us to solve it nicely with the previous techniques. So we want to address limits like this green one over here. The techniques that we're about to discuss will allow us to solve this limit rather easily. Okay. Okay, so that was 0 over 0, infinity over infinity. Once again, here we have our two limits. Certainly the red one is infinity over infinity. And as you remember, this is a rational function, so because the degree of the top is less than the bottom, this limit is 0. And in the blue one, still infinity over infinity, but now the top and bottom have the same degrees, so this is 2 over 4 or 1/2, because it's the ratio of the leading coefficients. Once again, what do we do with the green one? So this green limit, even though the techniques that we have discussed so far does not allow us to compute this algebraically, we can actually see what the answer is going to be because we understand from pre-calculus the relative growth of functions. I will talk about this a little bit on Wednesday because this will allow you to deal with limits like this rather quickly. For example, exponentials, they are among the fastest growing functions, okay? Then polynomials, and then lastly we have logarithms. In other words, ln is among the slowest growing function. So any polynomial beats ln when it comes to behavior at infinity. So ln is all of those. So natural log, polynomials, and exponentials, they go to infinity, right? Either positive or negative infinity when x approaches positive infinity. Let's say positive infinity in this case, because it really depends on the leading coefficients, etc. But they approach to some type of infinity. Now, how fast do they do this? And what I'm saying is ln is the slowest, then comes polynomials, and then the fastest one is exponential. Okay, so in this case, in the green limit, we have a limit at infinity of ln divided by x. Because x is a polynomial, right? It's a line, so it's a polynomial. It grows faster than ln, even though this is infinity over infinity. The bottom is way faster than the top, so this limit is going to be 0. Okay? If it would have been written like this, now because the top grows way faster than the bottom, then this limit would be infinity, positive infinity. Okay? But anyways, the techniques that we're going to learn will allow us to compute this algebraically. But when you want to do something quick, you can just use the relative growth of function to quickly decide. Okay. Again, I will mention something like this on Wednesday because we don't have class on Monday. On Wednesday, so that we can clarify this because it's good to know this. Okay. So 0 over 0, infinity by infinity. We already knew those two anyways. So here is another one that we haven't discussed, which is 0 times infinity. Here we have two limits, our red and blue limits, and just taking a look at it quickly, we see that the red is indeed 0 times infinity, right? Because remember, e to the x, think about the graph of e to the x, when x approaches positive infinity, e to a negative x approaches 0. draw the graph of e to the x here. This is e to the x. So when the argument approaches negative infinity, it goes to 0. And when it approaches positive infinity, it goes to positive infinity. So this is 0 times infinity. But then, of course, you could multiply before you even take the limit. And so the e to the negative x cancel with e to the x, giving you e to the 0, which is 1. So this limit is just 1. Now on the blue limit, once again, 4 over infinity, that's 0, right? And then times x, that's infinity. So that's another 0 times infinity. But this time, of course, this limit is 4 because we can simplify the x's before we even take the limit. So these are silly examples, but they illustrate the purpose, okay? They both have the form 0 times infinity, but we cannot deduce what the answer would be because they give you different results. Again, we would like to address something like the green limit, okay? Once again, the green limit can be solved using the relative growth because this can be written as square root of x over e to the x, and e to the x grows way faster than square root of x, and because this limit at infinity, because this limit is at infinity, then the bottom grows faster than the top, so this ultimately is gonna be 0, okay? All right, but again, we will do that nicely algebraically anyways. So that was 0 times infinity. Next, we have 0 to the 0, and then we have a red and blue limit. So the red limit, hopefully you see that it's 0 to the 0. But then, of course, notice that here x is not equal to 0. We're getting close to 0. So if you simplify this before you take the limit, any non-zero number raised to a 0 power, that's always equal to 1. So this limit is 1. While the blue limit still 0 to the 0, but this time this is just 0. Because 0 to the x, that's just 0, right? Remember, x is not equal to 0. We are getting close to 0. And for example, we would like to deal with something like this green limit. This one now is not as easy as the previous ones that you could use relative growth. Here, there is some work that needs to be done. Okay. Okay. That was 0 to a 0, infinity to a 0. Here in the red limit, you can see here is infinity to a 0. But then, once again, 1 over x to a 0, that's going to be 1. So this limit is equal to 1. Here is another example of infinity to a 0 in our blue limit. But this time, this limit is equal to e, because you can cancel the x's when you multiply the exponents, and then just get a constant. Okay, you would like to calculate something like this green limit. It's a little bit more complicated than the previous ones. This one we can do it with the substitution technique that I explained at the beginning of the semester. For example, a limit like this showed up in the first exam. Okay, but today we're gonna learn another technique that will allow us to streamline this process, and we don't have to rely on the substitution. We can actually compute this slightly more directly. Okay, so 1 to the infinity, the red limit over here. Remember, this is e, right? That's the definition of e. And then our blue limit, we can simplify before we take the limit, so we get e to the negative 2. So once again, indeterminate form. Why is 1 to the infinity in indeterminate form? Because here we have two limits, both of which give you 1 to the infinity when you directly evaluate it, but each of them, but they give you different results ultimately. One equals e, the other one equals e to a negative 2. Therefore, just having 1 to the infinity is not enough. You cannot deduce the final answer from there. You need to do something. Okay? That's the moral of the story. Any time that any of these forms show up, you have to do something. Here we have a green limit that, similar to the one above. And then finally, we have infinity minus infinity. Okay? So it's the difference of two expressions, each of which give you infinity. So for example, here we have a red limit. If we want to calculate this, what we should do is combine like terms. So, and just subtract the two things. So let's see, that's 2x times x plus 2 minus x squared plus 1. And then we can distribute. So that would be 2x squared plus 4x minus x squared minus 1 over x plus 2. So this gives us limit as x approaches infinity of x squared plus 4x minus 1 over x plus 2. And because this is a rational function, the degree of the top is bigger than the bottom, then this limit is positive infinity. That's our red limit. Now our blue limit is a silly one, right? Infinity minus infinity. But of course, you have x minus x. So this is just 0. So we can see how we have these two limits. They both have the form infinity minus infinity, but they yield different results. Again, we would like to deal with something like this green limit as well. Okay. All right. So what I've just done is justify to you why these 7 forms are called indeterminate forms of limits. Okay. So you need to know this. You have to, because you need to be able to recognize that you are in the presence of an indeterminate form. Okay. So if any of these forms show up, it means you need to do something. You cannot just leave it like that. You cannot deduce the answer from there. Okay, so now we're gonna move on and address each of these and see how to deal with these situations. Okay, what's gonna happen is that we're gonna have a systematic way. We're gonna have a theorem that will allow us to deal with 0 over 0 and infinity over infinity forms. Okay, that's called L'Hopital's rule. So we're gonna discuss that pretty soon. And then once we know L'Hopital's rule, we're gonna discuss how we deal with the rest of the indeterminate forms, okay, with the remaining 5. And what's gonna happen is that in one way or another, the other 5 we can do some manipulation, we can do some algebra and manipulate them so that we turn them into either a 0 over 0 or infinity over infinity situation. And then ultimately we'll be using L'Hopital's rule. So really, L'Hopital rule is the key here when it comes to dealing with indeterminate forms, okay? So let me talk about L'Hopital's rule. Okay, so so we don't waste time, I'm just gonna go ahead and write down the theorem, and then I'm gonna show you how to use it in some examples, okay? All right, so theorem, this is L'Hopital's. So L'Hopital's rule, here's what it says. So suppose that you have two functions. So let f and g be two differentiable functions on an interval a b containing the point c. Okay, so containing c, and except possibly at c. In other words, they don't have to be differentiable at c themselves, except possibly at c. Okay, also let's assume that the derivative of g is different than 0. Okay, so assume the derivative of g is not equal to 0 on this open interval, except possibly at c. So at c, anything can happen. But around c, everything has to be nice. That's what we're trying to say here. So both f and g are differentiable functions around c. At c themselves, we don't really care too much. And then the denominator g cannot be 0 around c. Okay? So when this happens, then we have the following statement. So if the limit as x approaches c of f over g. So the limit as x approaches c of f over g gives either 0 over 0 or infinity over infinity in any of its forms. So So I'm gonna actually spell them all out. So infinity over infinity, then negative infinity over infinity, or negative infinity over negative infinity, or infinity over negative infinity. So if any of these forms happen, so remember all of these colloquially, we just refer to them as infinity over infinity, okay? From now on. So whenever I say infinity over infinity, I mean any of these four. So if this limit gives 0 over 0 on infinity over infinity, then we can actually replace this limit by the limit of the derivative of the top and bottom. So then the limit as x approaches c of f over g equals the limit as x approaches c of f prime over g prime. Of course, provided that the limit on the right exists. Okay? So as long as the limit on the right hand side exists. Okay, so moral of the story, L'Hopital rule says that when you want to take a limit, if this limit gives you 0 over 0 or infinity over infinity, what you can do is replace the expression that you have by the following: take derivative of the top and then derivative of the bottom and calculate the limit. Okay, so that's all it says. So you can replace the top by derivative and the bottom by derivative. Now be careful, this is not quotient rule. There is no quotient rule happening here. Okay, L'Hopital rule says is you can replace the top by its derivative and replace the bottom by its derivative, and then continue taking your limit. And another detail here is that here I'm using the value c, but this statement actually holds also for side limits and also if c itself is infinity. So remark, this statement holds for x approaching c from the right, x approaching c from the left, and also x approaching positive or negative infinity. Okay, so it doesn't have to be approaching a certain point from both sides. It could be side limits or also it could be infinite limits. So you can use L'Hopital rule in any of these situations. The important thing is that it has to give you this type of indeterminate form, either 0 over 0 or infinity over infinity. Okay, all right, so let's do some examples. So we can see how to use this. For example, let's do our sanity check. Okay, as a first example, let's do the limit as x approaches 0 of sine of x over x. And why am I doing this? Well, because we already know what the answer is, right? We argue from before, remember, using squeeze theorem and so on, this special limit, and we argue that this limit was equal to 1. Well, it turns out that this limit also is of the form 0 over 0, so we could do it using L'Hopital's rule. So let's make sure that we do indeed get 1. So let's see. This 0 over 0 situation, right? It's 0 over 0. So I'm going to be using L'Hopital rule. So every time that I use L'Hopital rule, I'm going to write LH. I want you to write LH on top of the equal sign when you're about to use L'Hopital rule. That way I know what you're doing. Okay? So this is 0 over 0. So we're going to use L'Hopital's rule. So L'Hopital rule says that I can replace the top by its derivative. So instead of sine, I do cosine, and the bottom by its derivative. Derivative of x is 1. Let me actually at least, so for one time, I'm going to write this. Normally, we just write the result, okay, of the derivatives. But so you see what I'm doing. So this is what L'Hopital rule says, that you're allowed to replace the top by its derivative and the bottom by its derivative. In other words, this becomes the limit as x approaches 0 of cosine, oops, this is an x in here. So of cosine over 1, and then certainly when you take this limit, cosine of 0 is equal to 1. So this is 1 over 1, which gives you 1, as expected. Okay. Now let's use this idea to compute other limits. So for example, let's do e to the x minus 1 over x. That's one of the green limits that we have from before. So limit as x approaches 0 of e to the 2x minus 1 over x. Okay, so in this case, certainly when you plug in, you get 0 over 0. So we know that we can use L'Hopital's rule, and let's do so. So this becomes the limit as x approaches 0. Now, we need to replace the top by its derivative. What's the derivative of the top? That's going to be e to the 2x times 2, remember the chain rule, okay, divided by 1. And so what's the answer here? Well, this is just equal to 2 times 1 over 1, which is just 2, right? Just remember, e to the 0 is equal to 1. Okay, so let me write it in the same order that I have the factors so you can identify it. So e to the 2x, when x approaches 0, will give me 1, and then 2 is a constant, so we have it there. So you see how straightforward it is to compute this limit, okay? For example, let's do limit as x approaches infinity of ln of x over x. This was the one that we were claiming that was going to be a 0, right? Because x grows faster than the natural log. Well, let's see it now. Again, this is infinity over infinity, so L'Hopital's rule can be used. So that would be limit as x approaches infinity. Derivative of the top is 1 over x. Derivative of the bottom is 1. So this is just 1 over x, really. And then, as you know, the limit as x approaches infinity of 1 over x, that's 0, as predicted. Okay, so we have that. Let's see, let me actually do one more. A limit as x approaches negative infinity of x squared over e to the negative x. So notice that this limit, the top goes to positive infinity and the bottom also goes to positive infinity, because when you put negative infinity on the negative x part, that becomes positive infinity, and then e to the infinity is just infinity. So using L'Hopital's rule, we get limit as x approaches negative infinity. So let's see, derivative of the top is 2x, derivative of the bottom is e to the negative x times negative 1, right? Chain rule, remember. Now, notice that here, we still have infinity over infinity. So that means that sometimes you may need to use L'Hopital rule more than once. Okay? So here we still have infinity over infinity. So we're going to use L'Hopital rule again. The point is that when we do it again, the infinity in the top is going to be gone, right? Because now derivative of the top is just 2. Derivative of the bottom is going to be e to n minus e to a negative x times another negative 1, making it positive. So we get just e to a negative x, and now 2 over infinity, this is finally 0. Okay, once again, because the bottom is an infinity and it's an exponential, you could have done from the beginning and say, well, exponential grows faster than polynomials, so we know the bottom grows way faster, so this would be 0. But again, this is using a different type of analysis, the relative growth of the function. Okay, so this is how we deal with infinity over infinity and 0 over 0. We just directly use L'Hopital's rule. Okay, so now the question is, okay, but how do we deal with the other indeterminate forms? So let me discuss this. Remember, you need to know the indeterminate forms. So let me show you what is the idea. So recall, indeterminate forms are 0 over 0, infinity over infinity. You need to memorize this, okay? You need to know this. You need to be able to identify them. Then comes, so these are the quotient types, the first two. Then comes the other three, 0 times infinity, that's the product type, okay? Then comes the exponential type, 1 to the infinity, 0 to the 0, infinity to the 0. and then comes one that is infinity minus infinity. Okay. Now, there's a reason why I write them in this order. Okay, so I strongly encourage you when you are studying, like write them in this order so you can be able to understand how to solve them actually, because that's why I'm writing it like this. So let me show you the diagram here. What's the strategy? The idea is that the first two we know how to deal with them. They are done via L'Hopital's rule. Okay. Now, what do we do with the next one, with the 0 times infinity? Well, what we do here is we do a trick. So we take this 0 times infinity, and then we do a trick to it, and we turn it into one of these two, either 0 to the 0 or infinity over infinity. And then we use L'Hopital's rule. Okay? I'm going to show you what the trick is. In fact, let me do that right now. So the trick is, so when you have 0 times infinity, here is a trick. So I'm just gonna manipulate. Remember, really, this is not really a zero and this is not really infinity. Zero here represents an expression, a function whose limit is zero when you get close to whatever you're approaching to in the limit. And the second infinity here represents a function whose limit is infinity. So before you take the limit, you can actually manipulate these things. You can divide, you can move things around. So in particular, I can rewrite this as 0 over 1 over infinity. In other words, the infinity that's multiplying the term, the infinity is multiplying the 0. I can bring it to the denominator as 1 over infinity. Okay? So basically, I'm just using the fact that if you have a times b, so, a times b, this can be written as a over 1 over b. Okay? But also notice that you could write this as b over 1 over a. In other words, you can decide what you want to bring to the denominator. So I could also rewrite this as leave the infinity on top and then write it as 1 over 0. So why is this helpful? Well, because notice that this now has the form 0 over 0, or this one over here has the form infinity over infinity, right? So we will be in a position to use L'Hopital rule at this point. So that's the trick, okay? So every time that you have 0 times infinity, you will turn it into either 0 over 0 or infinity over infinity. Which one? Well, it depends on the function. Like for example, my advice to you is if one of these terms is if the 0 or the infinity, one of them is an ln, just leave it alone. Leave that one on top and then bring the other one to the denominator. Because if you bring the ln to the denominator, you're going to have 1 over ln, and using L'Hopital rule there, it's not going to be pretty because taking derivative of 1 over ln is not a nice job. It's easier to just take derivative of ln. So that's why we just leave it on top. Okay? We see in the examples. So how we deal with 0 times infinity? That's the trick. Now, for the other three, 1 to the infinity, 0 to the 0, and infinity to the 0, which are the exponential likes, well, we deal with them in a similar way, in the same way. Each of what we do to one, we do the same thing to the other two. So we do a trick, and that trick is going to turn them into a 0 times infinity situation. And once we have a 0 times infinity, we already know what to do to then go to the first two, either 0 over 0 or infinity over infinity. Okay, and then ultimately we use L'Hopital rule. Hopefully you see here why L'Hopital rule is the key. Okay, everything at the end boils down to L'Hopital's rule. Let me explain what the trick is. All right, so 1 to the infinity. Well, the idea is that we're gonna use ln, right? So we want to get rid of this exponential behavior. Let's use the property of logarithm to be able to bring it down. Now, I like to do this in one line instead of, some people do it like in some places you're going to see it similar to the logarithmic differentiation part. Like you call it y equals your function, then you take ln on both sides and so on. I prefer to do it directly. So I'm going to be using the following property that if you have, let's see, if you have x, let me just write something. So if you have x, whatever x is, okay, this can always be written as e to the ln of x, okay? In other words, any expression that you have, you can always write it as e to the ln of that expression. Of course, provided that the expression itself is positive, because you cannot do ln of something negative, okay? All right, so I want to take advantage of this property. Why? Because now 1 to the infinity, I can write it as e to the ln of 1 to the infinity. Okay, I'm just basically using the property that I just mentioned. The fact that because exponential e and ln, they cancel each other, remember. E to the x and ln of x, they cancel each other. They are inverse functions. So now what we can do is, why are we bringing ln? Because now we can bring this guy down, right? So this now becomes e to the infinity times ln of 1. And remember that the exponential e is a continuous function. So when you are calculating this limit, it actually, you pass it through, and the question is really about the limit here. And then remember that the answer would be e to the power of whatever this top limit is. Now, if you look at this, what type of limit do we have here? We have an infinity times ln of 1, but ln of 1 is 0. So this is infinity times 0. Okay, so here we have our 0 times infinity situation. As promised, we turn it into the 0 times infinity. Now here you would do the trick that we described above to turn into either 0 over 0 or infinity over infinity. And then you use L'Hopital's rule. Okay? All right, so 0 to a 0 is a similar business. E to the ln, 0 to a 0. Bring it down in front of the ln. Now remember, uh, when the argument of the ln approaches 0 from the right, okay, from the right, then ln goes to negative infinity. So this is a 0 times infinity situation. It's really 0 times negative infinity, but again, that's just 0 times infinity. Remember, uh, when we say 0 times infinity, it can be positive or negative infinity. So we use the same trick as before to turn into either 0 over 0 or infinity over infinity. And then finally, the infinity to a 0, we do the same thing. This time, the 0 comes in front of the ln. But, ln of infinity is just infinity as well. So this now is 0 times infinity once again. Okay? So this is a trick. You turn the indeterminate form that is exponential-like into a 0 times infinity type by doing this manipulation. And then you do another trick to turn it into 0 over 0 or infinity over infinity, and then you take the limit. As I advised you above, notice that there is always a term here with ln. So what you should do is keep that guy along. The ln, you leave it there, and then what you bring to the denominator in the trick of 0 times infinity is the other one. Okay? So for example, let me move this a little bit. So for example, here you have infinity times ln of 1. Just keep the ln of 1 in there, and then bring the term with the infinity down to have a 0 over 0 situation. Okay? Here you have 0 times ln of 0. Just keep this term in here and then bring the 0 down. So you're going to have an infinity over infinity situation. And here you have a 0 times ln. Just keep the ln of infinity in the top and bring the 0 down. That will give you an infinity over infinity situation. Okay? And now, L'Hopital's rule. Okay, so this is how you address the three exponential type indeterminate forms. And then we have the last one, the infinity minus infinity. This one is on its own. Okay? So this one is on its own. So what you do here is, so I will say here on its own. So what you do here is you go ahead and you subtract, right? These are two expressions. So the idea is that you're gonna subtract the two expressions, or sometimes you're gonna subtract. So what you do is you factor something, and it will reduce to one of the previous one. So it is subtract or factor, then solve. Because what's gonna happen is that when you subtract or you factor, you're gonna reduce it into one of the previous ones. Okay? So for example, just to show you, if you have infinity minus infinity, let me call this an infinity 1, infinity 2. Okay? So if I factor out the infinity 1, then we're gonna have 1 minus infinity 2 over infinity 1. So, we turn this into an infinity over infinity situation. You will solve that one, and then once you solve that one, you see L'Hopital root, then you see what you get. If this happens to be 1, then it will be a 0 times infinity, so you will need to do something else, right? Another trick. Or you could factor, the infinity 2 first, and then you will get this. And then again, you repeat the same process. Okay, so this is the factoring technique, but sometimes you don't even need to factor. You just, these are two fractions sometimes, and then you just subtract them, as you saw, as we did before in the previous example when we're talking about indeterminate forms. Subtract them and then deal with what you have. Okay, I can show you what I'm trying to say here. You see here, when we did the red limit, this is infinity minus infinity. All we did was, okay, we subtracted the two expressions, and then it turns out that we ended up with a rational function, and then this was an infinity over infinity case, and then we just calculated, and it turns out that it was positive infinity. Okay, so for example, in this green limit, which we will do it, what I would do is I would subtract this first. I wouldn't factor anything. I would subtract this first, and then see what I obtain. Okay, then I will do an example in which actually there is nothing to subtract, so you have to factor. Okay, that's why I was mentioning two ideas. Okay, so these are the techniques. So let us now do some examples to illustrate how to use these techniques. Okay, again, try to have, this diagram is very important, what you see here at the top. You have your 7 determinate forms and how to deal with them. First two, L'Hopital rule. 0 times infinity, do the trick to turn into 0 by 0 or infinity over infinity. And then L'Hopital rule. The other three that are exponential type, do a trick to turn into 0 times infinity. This trick involves using ln, okay? And then once you have 0 times infinity, do another trick to turn into 0 by 0 or infinity over infinity, and then L'Hopital's rule. And then finally, you have infinity minus infinity, which is on its own. Okay, so let's do examples. For examples, find the limits. And let's see, let's do limit as x approaches infinity of e to the negative x times the square root of x. So the purpose here is to do the green limits, okay, times square root of x. So this limit is 0 times infinity, but there is actually an obvious way to deal with this limit. You can just rewrite it as square root of x over e to the x, right? Because you have e to the negative x, so you can bring it to the bottom. So now we turn into infinity over infinity. If you think about it, you can say that we used the following trick. What we really did was that we rewrite this as square root of x over 1 over e to a negative x. But 1 over e to a negative x, that's just e to the x. Okay? Okay. So this is infinity over infinity, so now we can use L'Hopital's rule. By the way, here you can see what the answer will be, right? Because e to the x grows faster than the square root, so we're expecting this to be 0. But let's see. So derivative of the top is 1 over 2 square root of x. Derivative of the bottom is still e to the x. So then this becomes limit as x approaches infinity of 1 over 2 square root of x times e to the x. So now the entire infinity was translated to the denominator. So we have 1 over infinity, which is 0, as expected. Okay, now let's do limit as x approaches 0 from the right of x times ln of x. So notice that this limit is of the type 0 times negative infinity. So it's 0 times infinity. Remember, when the argument of ln approaches 0 from the right, it goes down to negative infinity, the ln. Okay. So here you need to bring one of the two terms to the denominator to turn it into 0 by 0 or infinity by infinity. My advice is leave this guy there. So the other one is the one that we're going to bring to the bottom. Okay, so ln, we don't touch it. We leave it in the top. And then the x, we bring it to the denominator as x over x. So this now has a form infinity over infinity. So we can take the L'Hopital's rule, and let's see what we get. So that would be 1 over x, derivative of ln is 1 over x, and the derivative of 1 over x is negative 1 over x squared. Okay, so simplifying here, we get limit as x approaches 0. So let's see, the x squared comes to the top, so it's going to be negative x squared over x. The x's cancel out here, so we get limit as x approaches 0 from the right of negative x, and this limit is just 0. Okay, all right, so we have done some 0 times infinity cases. Now let's move to the exponential likes. These are the ones that are a little bit more algebraically involved. Okay, so let's do limit as x approaches infinity of 1 plus 3 over x to the 5x. So notice that this is, so what is this? When x approaches infinity, so 3 over x is 0, so that's going to be 1 to the infinity. Okay, so let's activate the process. So the trick is that we write this as e to the ln of 1 plus 3 over x to the 5x. And remember, the idea for doing this is because now we can take this guy and we can bring it down here to the front. Okay, so this becomes limit as x approaches infinity of e to the 5x times ln of 1 plus 3 over x. Now, because exponentially is a continuous function, we can pass the limit through. So this is going to be e to the limit of the exponent. So my result is going to be whatever this limit is, but then the answer is e raised to the power. So here's what I'm going to do. I'm going to write here e to the power of, and put a box here, because then inside that box, that's where I'm going to put the result. And just to have things cleaner, I'm going to go ahead and take that limit. So this limit over here, I'm going to evaluate it down here. But remember that the answer is e raised to whatever this limit is. Okay, a common mistake that students make is that you will do this, compute this limit, and then tell me that the answer is whatever the limit is. No, it's e to that number. Okay, all right, so what do we have here? That's infinity, and then the ln part gives me ln of 1, which is 0. So that's infinity times 0. So this is a 0 times infinity situation, and we know how to deal with this case. We take one of the terms and bring it down, ln. I'm going to keep it in the top, and the other one I'm going to bring it down. So, okay, the 5 is really not important, so I'm just going to keep the 5 here. The 5 is not really bothering me. But I'm going to keep the 5 here because that just makes things easier. Just going to bring the x down. Because if I bring the entire 5x down, then you have to use chain rule in the denominator as well, and so on. Well, not necessarily chain rule, but the constant rule. But anyways, 5 is just a constant. It's not really affecting anything, so I'm going to leave it there in the top. Okay, so now let's use L'Hopital's rule, because we have a 0 over 0. So remember, there's a 5 in the top, so I'm just going to keep it there. And then when we take derivative of ln, that's going to be 1 over 1 plus 3 over x, remember chain rule, times derivative of the inside, that's going to be negative 3 over x squared. Okay, and then in the denominator we have derivative of 1 over x, which is negative 1 over x squared. Okay, so now we simplify. So let's see, the negatives here, they cancel out. So here we have an x squared that comes to the top, and it will cancel with this x squared down here. Okay, so we get limit as x approaches infinity of, let's write down the expression. Let's see, 5 times 3, that's going to be a 15. And then here we have 1 plus 3 over x. So this is what we obtain. And when we take the limit, you can see that this little part here goes to 0, the 3 over x. So we get 15 over 1 plus 0, which is 15. Now remember, the answer is not 15. The answer is e to the 15. Okay? So e to the 15. So these are the ones that are a little bit more algebraically involved, because since they have this ln, and when you take derivative, you have to be careful. It's typically chain rule involved. So make sure that you're okay with that. All right. So let's do another one. That was 1 to infinity. Let's do another one. For example, limit, and that was at infinity. Let's do it approaching 0. Approaching 0 from the right of 1 plus 2 over x to the 3x. Okay, so again, this is 1 to the infinity, so I'm gonna do a 3. So limit as x approaches 0 from the right of e to the ln of 1 plus 2 over x to the 3x. So bring the 3x down. In front of the ln, but remember, you keep it up there in the exponent, and then we pass the limit through. So this is e to the power of whatever this limit is. And we can do this because remember, exponential is a continuous function. So continuous function, you can pass the limit through. Remember, my answer is going to be e to whatever the result of this limit is. So let's compute the limit now. Okay, so we have this. So this is a 0 times an infinity situation. So this is going to be, I'm going to leave the ln in the top. 1 plus 2 over x, and then again as before, I'm going to keep my 3 here and then just bring the x down. So using L'Hopital's rule now, we get limit as x approaches 0. Did I write L'Hopital's rule before? No, let me write LH. Okay, limit as x approaches 0 from the right. Let's see, derivative of the top is 3 times 1 over 1 plus 2 over x, and then times derivative of the inside, which is negative 2 over x squared. Then here in the denominator, this is negative 1 over x squared. This is very similar to the one above. The minus cancel out. These x squares cancel out. So we end up with limit as x approaches 0 from the right of 6 over 1 plus 2 over x. Okay, so when you take the limit, this part right here goes to 0. Nope, doesn't go to 0. So let's see, this part right here goes to infinity. It's different. Remember, this limit is x approaching 0 from the right. So this part here goes to infinity, positive infinity. So the denominator is infinity, so 6 over infinity, that's a 0. Okay, so this limit is 0. So here we get e to the 0, and e to the 0 is equal to 1. Okay, good. So this we have 1 over 1 plus 2 over x times derivative of the inside, which is negative 2 over x squared. Yeah, just like that. All right, so we have this example. Then let's see, let's compute another one. How about, so that was number 4. So let's see, number 5. Let me look for the example here. Okay, so let's do sine of x to the x. So limit as x approaches 0 from the right of sine of x to the x. So this is a 0 to a 0 case. Okay. All right. So in this case, that's 0 to a 0. So we activate the process. Okay, so I'm gonna do this a little bit faster. So as you know, we write it as e to the ln, but the upshot is so that the x comes down. So I'm gonna write that already. Okay. And so this is gonna be e to the limit of x times ln of sine. Remember, my answer is e to whatever that limit is. So let's compute the limit. Limit as x approaches 0 from the right of x times ln of sine plus ln of sine. I'm gonna bring the x down. So now this becomes sine of 0 is 0. So that's gonna be infinity over infinity because ln of something approaching 0 is infinity. And we can use L'Hopital's rule. Here we have infinity over infinity. So this is limit as x approaches 0 from the right, so derivative of the top. So remember, u prime over u. So it's going to be cosine over sine. And then this is negative 1 over x squared. Okay, so let's see, what do we obtain here? As limit as x approaches 0 from the right. And we're going to have negative x squared times cosine over sine. Okay, so let's see, in this case, when we take the limit, this is a 0 over 0. So again, the problem was not solved, so we need to keep using L'Hopital's rule. So I'm going to use L'Hopital's rule again. And notice that now we need to use a product rule in the top. Okay, so let's see. Derivative of the first is going to be negative 2x squared, negative 2x times the second plus the first function times the derivative of the second, negative sine. And then the denominator is derivative of sine, that's a cosine. Okay, now here we're good because cosine of 0 is 1, so now we don't have a 0 in the bottom anymore. So when we take the limit, let's see, this part right here becomes 0. This part here becomes 0 because of the x, and this part here becomes 1. So this limit is 0 plus 0 over 1, so that's equal to 0. So the answer, remember, this is not the answer. The answer is e to the 0, so that is 1. So be careful. Remember that here, down here, we're just computing this top here, this limit. But then the answer is e to whatever the result of that limit was. Okay? All right. So I will do a couple more examples on Wednesday, just so that we do that live in person, in case that you have a question to ask me. So let me just do now, let me go to the infinity minus infinity type. Let's see, number 6. Let's do limit as x approaches 1 from the right of 1 over ln of x minus 1 over x minus 1. Now here you have to be very, very careful on how to compute this limit. So you need to be able to identify what type of limit it is. So let's see. So ln is approaching 1. So x approaches 1, so ln approaches 0. So 1 over 0 is infinity. So the first one is infinity. Now the question is it positive or negative infinity? And it depends on one side. We are approaching 1. So let's look at the ln function a little bit more closely. This is the ln function, and this point right here, the x-intercept is 1. So we're approaching 1 from the right. So when you approach 1 from the right, ln gets close to 0 with positive numbers. Okay, so that would be a positive infinity. So this one here give me positive infinity. Because if we did it from the left, it would be negative infinity because it's approaching 0 from below the x-axis. So it will be negative infinity. Okay, so you have to be careful. So this one is just positive infinity. And then because x is bigger than 1, x minus 1 is positive. So the second one is also positive infinity. So we do have infinity minus infinity. Okay. So what I'm going to do is I'm just going to combine these two. So x minus 1 times ln, and then this becomes x minus 1 minus ln. And then let's see what we have here. So when we take the limit here, that's going to be 0 on top and 0 in the bottom. So a 0 over 0. Okay. So this is a 0 over 0 situation. So I'm going to use L'Hopital's rule. As promised, when you combine them, you're going to get one of the previous forms. So let's see, what's the derivative of the top? The derivative of the top is going to be 1 minus 1 over x. And then the derivative of the bottom, we do a little product rule. So this is going to be the derivative of the first, that's a 1, times the second, plus the first, times the derivative of the second. Okay, so now let's simplify this. I'm going to multiply top and bottom by x to clear all those little denominators. So this becomes x minus 1 over x ln of x plus x minus 1. Okay, so when we take this limit, what's happening here? Okay, so still we have 0 over 0, right? So I'm gonna use L'Hopital's rule one more time. So let's use L'Hopital's rule. So we get limit as x approaches 1 from the right. This time the derivative of the top is just a 1. And then in the bottom, we need to do another little product rule. So as gonna be ln of x plus x times 1 over x. That's the product rule for this little part right here. And then plus 1, because the derivative of x minus 1. Okay, so now these things cancel. So we get limit as x approaches 1 from the right of 1 over ln of x plus 2. And when x approaches 1, then we get 1 over ln of 1 plus 2, which is 1/2. So the answer, because ln of 1 is 0. So this limit equals 1/2. And then to close, let me do another one in which combining is not good enough. So you do need to do the factoring that I was mentioning earlier. For example, how about e to the x minus x as x approaches infinity? So this is infinity minus infinity, but you see here there's nothing really to combine. Okay, so what I'm gonna do is I'm gonna factor out e to the x, and then we're gonna have 1 minus x over e to the x. And then let's deal with this limit. Okay, well, what is the limit? I mean, at this point, you could do this very quickly using the relative growth. Exponential grows faster than polynomial when x approaches infinity. So because exponential is in the bottom, that limit would be 0, that fraction over there. But if you don't want to do that analysis, you can do it using L'Hopital's rule. It's a little L'Hopital's rule here, infinity over infinity. So the derivative of the top is 1, the derivative of the bottom is e to the x. So now 1 over infinity, that's a 0. So this part right here goes to 0. So that means that the parenthesis goes to 1, and then e to the x goes to infinity. So infinity times 1, that's infinity. So this limit is positive infinity. Okay? All right, guys. So go over these examples. Make sure that you understand this. The ones that are a little bit more algebraically involved are the exponential lights, as you can see. So, practice with the homework that are also in the book. You can find more problems. And, as usual, if you have any questions, uh, you're welcome to ask on our next class. Okay, bye.